Welcome everyone. Today we're diving into a super innovative modular cabin design that's truly game-changing. Think rapid deploy graphene shelters.
Absolutely. It's fascinating how they've managed to consolidate so many crucial elements into a lightweight modular cabin.
Right, so we're talking about a compact structure with a 4 by 4 meter footprint, 4-meter high walls, and an added gabled roof. This design not only improves rain and snow shedding, but also packs in an incredible level of structural
Yep,
integrity.
exactly. And what's really cool is the way they reduce complexity and weight using those 4 mm composite panels. They even mold the locking mechanism and load-bearing supports directly into the panels.
It's like they're building a skeleton that's integrated straight into every panel. The whole idea revolves around eliminating screws, bolts, or glue in the main assembly, relying instead on a high-tolerance key and keyhole interlocking system.
Yeah, so how does that work exactly with the interlocking keys?
Well, the edges of all the wall, floor, and roof panels have a recessed channel on one side paired with a rib on the other side. Two people can align the rib into the channel and then, using a simple rubber hammer, give it a tap which secures the joint, creating a weather-tight, super rigid structure that's almost like a monocoque shell.
Mm-hmm. That's pretty ingenious, eliminating the need for extra hardware. But what about the floor and mezzanine? How do they ensure the whole building is anchored properly?
The floor is the anchor base, a neat 4 by 4 meter panel with heavy-duty, reinforced metal loops molded directly into its corners. They connect these loops to earth screws, long, heavy-duty spirals driven right into the ground, which secure the cabin against winds, earthquakes, and even theft.
Absolutely, that adds a lot of stability. And the mezzanine sounds super clever too. It's almost like a built-in second floor, right?
Exactly. The mezzanine is about 75% of a full floor, roughly 12 square meters, that slots directly into molded supports in the walls. They've designed the wall panels with a deep groove about 3 meters from the base for this purpose. You get an open, post-free downstairs area, and access is granted via a lightweight composite
That's really
ladder
smart.
that hooks onto the mezzanine edge.
It seems like every element is designed for quick and efficient assembly. How fast are we talking?
The entire building can be assembled by a small team in just a few hours with minimal tools. You start by anchoring the floor, raise the walls using the snap-fit lock, install the mezzanine, finish up the roof with gabled panels that naturally shed water and snow, and then hook up the ladder. It's rapid deployment at its finest.
Yeah, that's impressive speed. And the roof design plays a big part too. The gabled roof not only offers higher ceilings upstairs, but it exactly tackles the issues of heavy rain and snow, right?
Absolutely. The roof comprises 4 large sloped panels that interlock at the peak, providing both aesthetic appeal and practical functionality. It's all about blending engineering elegance with real-world performance.
Yep, makes sense. Now, when it comes to cost, I see there's a detailed breakdown. The material costs are based on competitive composite material prices in the automotive and construction sectors, correct?
Yes, they've targeted a cost-efficient mass market using low-end, mass-produced carbon fiber composite ranges, something like $15 to $25 per kilogram for the finished panels. The overall production cost, including assembly hardware, comes somewhere between $6,260 and $10,100 per unit, which is actually competitive with traditional materials like 4 mm thick aluminum composite panels.
That's a solid competitive edge. It's also really interesting that the material offers superior strength, fire resistance up to 250 degrees Celsius, and it's waterproof and UV resistant. That kind of performance is not common, right?
Exactly. The design not only ensures high durability and resistance to natural disasters like earthquakes and hurricanes, but there's also an armored version available. The armored variant is resistant to high-level blasts and ballistic impacts. though it does come at a heavier weight and higher cost, something like $29,000 to $80,000.
True, though that trade-off might be acceptable in high security or military contexts. Speaking of cost, the transition from prototypes to mass production is a huge leap. The prototype chassis cost is astronomical compared to the mass production estimates, correct?
Absolutely. Prototype or low-volume production units can cost between $100,000 and $250,000 per chassis due to expensive molds, high material costs, and labor-intensive processes. But on scaling up to around 50,000 units per year using advanced automation like high-pressure resin transfer molding, costs can drop dramatically to about $5,000 to $8,000 per chassis.
That's a drastic reduction indeed. It really highlights how automation and scale can lead to disruptive cost advantages. Now, did you note the broader market applications they discussed?
Yes, besides military and stationary shelters, the same composite material has so many other applications like electric cars, reducing weight to enhance range, RVS for improved efficiency and safety, even commercial trucks, where saving weight means more payload and lower fuel consumption.
It's like a one-material-fits-all revolution. And not to forget aerospace and marine sectors. Drones, satellites, small airplanes, and even boat hulls can benefit tremendously from this, right?
Exactly. The lightweight yet robust characteristics make it ideal for building components that need to be super efficient and durable. I mean, it's like comparing a high-performance sports car to a clunky old sedan. This material could be the sports car of structural materials.
Yeah, that's a vivid analogy. But I do have a bit of a critique. While the design and rapid assembly are impressive, I wonder about the real-world challenges of maintaining those interlocking joints over time in harsh environments. What do you think?
Good point. I mean, it's like asking if a snap-fit lock will still hold up after years of thermal cycling and heavy winds. Although the design claims weather-tight and structurally rigid connections, extensive field testing, especially for long-term durability, will be key.
That's a valid concern. Overall, though, the integration of design innovation, rapid automated production, and a strong cost advantage position this modular system as truly disruptive in multiple markets.
Absolutely. It's the kind of design that makes you reevaluate how we approach building structures. From rapid deployment in disaster scenarios to applications in high-tech sectors, it's revolutionizing material usage.
Yep, that's the future right there. This discussion really brings out the exciting interplay between advanced material science and practical architectural design, doesn't it?
It really does, and it's exciting to imagine how these innovations might change our built environment, making structures more efficient, safer, and environmentally friendly.
Exactly, and it's a perfect example of engineering meeting real-world needs. Well, that's a wrap for today's deep dive into modular graphene shelters and rapid deploy structures. Thanks for the engaging chat.
Anytime, it's been a real pleasure unpacking this breakthrough technology with you.